All right, as you can see, we're going to add to our skill set as far as factoring. We're going to learn something new today, factoring a difference of squares, factoring differences of squares. Some keys with the vocabulary here. Differences in squares. Difference obviously means that we're going to subtract, so you're always going to be looking for two terms being subtracted, one from the other. And then squares, what you're looking for is terms that could be a square of something else. And I give you kind of a visual representation of this. X squared would be a squared because I can take x times x, and that would give me x squared. 25 would be a square because 5 times 5 gives me 25. We're looking at perfect squares there. So notice a difference of squares. The example here would be x squared minus 25. This would be an example of a difference of squares. And after watching the video today and taking notes, you'll have an idea of how to factor polynomials that look like that. Before we get into that, we've got to check our background knowledge and make sure we're okay on foiling. That will be a huge part of understanding why this difference of squares works. Notice if I had the binomial x minus 8, x plus 8, we can simplify that. Remember, if I have similar looking binomials, we know we can combine like terms. And we actually talked about this specific problem because when I have something like x minus 8, x plus 8, something kind of unique happens here with our middle terms. Because we have the plus and the minus but the same number, not only can we combine these terms, but they're always going to cancel out. So I'm left with x squared minus 64, which again you see would be a difference of squares. Difference of squares with x squared and 64 being subtracted. Even if it's a little uglier on the binomials, the same process is still going to work. We'd have 4x squared here when we multiply the first terms. Then we have a minus 6x plus 6x. And then notice that plus 3 and times a negative 3 gives me negative 9. Again, those middle terms are going to cancel out, and I'm left with 4x squared minus 9. You see two terms being subtracted, so you might want to check and see, well, is this a difference of squares? Notice, I'm looking, what would I square to get 4x squared? And actually, if I took 2x times 2x, we already saw that that would give me 4x squared. And the same idea, if I took 3 times 3 and 3 squared, that would give me 9. So this means the same thing here. What we'll be able to do is recognize this pattern when given this binomial and actually get all the way back to that original factored form. That's what we're working on today. Here gives you the real overview, the quick idea, kind of the pattern that you're looking for to factor a difference of squares. If you have two terms being subtracted, look and see, are they both squares? Are they both the square of some term? And what I want to do then is I want to identify what that term is. So for example, you notice a squared. I want to identify what is it that I would square to get that first term. That will become the first term in each of my binomials when I write this in factored form. Same idea with the second term. I want to identify that b. What would I square to get the second term? And whatever that is that I would square to get the second term will become the second term in each of my binomials here. And notice it'll just be a plus b times a minus b in factored form. When you're all done factoring, your answers are going to look like this in that same form of a plus b times a minus b. It'll make a little more sense when we look at some examples. You see x squared minus 36. That's a binomial. That's subtraction. I have two terms being subtracted. That's a difference. So I want to check and see, is there something that I could square to get x squared? Well, I think that one's fairly obvious that if I squared x, I'd have x squared. So I know what that a will be when I'm looking at this pattern. That a is x because it's being squared to give me the first term. Now I need to find something that I square to get 36, which happens to be, as you know, 6. That would become my b term. So x is the a term, 6 is the b term. Then remember that pattern. It's always a plus b times a minus b. So in this case, it would be x plus 6 times x minus 6. Nice thing about this, we can always check these by foiling. If I take x times x, I get x squared. Notice I have a negative 6 plus 6, and then I have a negative 36. This middle term here will cancel out because I have a negative 6x plus 6x, and I'm left with x squared minus 36, which was the original polynomial that you got. I'll give you another example, a little trickier maybe, but again the same idea. If I have coefficients as well as variables, look and see what could I square to get the coefficient, and then what could I square to get the variable. What could I square to get the coefficient, and what could I square to get the variable. To square to get 16, I know I need a 4. And then what would I square to get a squared? Well, that'd be a. So I've found my a term here. It's going to be 4a. In the second term here, 9b squared, I would square 3 to get 9. I would square b to get b squared. And so notice now I have my b term. And again, it goes into that pattern of a plus b times a minus b. So I'd have 4a plus 3b times 4a minus 3b. And if you don't believe me, you could surely foil that out, and you'll see you get back to that original two-term polynomial, that difference of squares. A great example here to star in your notes, just because it's a little different. Again, we see two terms being subtracted, so we think, hey, this might be a difference of squares. But then we look at it and we see, well, I have an exponent of 3, and I have just a g, and I have a 3. There's some weird things going on here. I don't think this is actually a difference of squares. Well, think back to your background knowledge here. What must you look to do first? You might need to factor out a greatest common factor, and that's actually the number one thing to look to do anytime you're factoring polynomials, is see if you can take something out first. And so notice I'm looking for the greatest common factor of 27 and 3, as well as g cubed and g. And so notice from last week, should be able to take out a 3g. That leaves us 9g squared minus 1 in parentheses. Now that I've factored out a 3g, if you look at the terms in the parentheses, you do have a difference of squares, and I can factor that as a difference of squares. What would I square to get 9? Well, I would square 3. What would I square to get g squared? That'd be a g. And then notice the square root of 1. What would I square to get 1? Well, 1 squared is 1. So I would have 3g plus 1 times 3g minus 1. The big trick here would be to not forget that other term that you factored out. That comes down below, and I'd still have 3g in my answer. Again, if you don't believe me, by all means, you could actually FOIL that out and then distribute a 3g, and you will get back to that original situation that you were given, 27g cubed minus 3g. One last example, good for a couple reasons. It's an equation that you're going to have to solve. We worked on that a little bit last week and on the quiz. And also you'll see that this is kind of a unique situation where I like the order to always be a plus b, a minus b when we're factoring, because we want to factor completely, and you'll see what I mean when we do this. Think back to the zero product property. We said if a times b equals 0, then either a equals 0 or b equals 0. To solve this equation, then the first thing we'd probably need to do is get it set equal to 0, and I'd subtract 16 on both sides. That gives us b to the 4th minus 16 equals 0. Should notice that it looks like we have a difference of squares. I know that I can square something to get b to the 4th, and that actually ends up being b squared. If I have b squared squared, that equals b to the 4th. So b squared will be my a term. And then what would I square to get 16? Well, I think we all know that that would be 4. And so notice, when I factor b to the 4th minus 16, I get b squared plus 4 times b squared minus 4, and that's still all set equal to 0. What I'm hoping somebody out there might notice, and this is again why I talk about why I like the order to be a certain way, I like the subtraction to come after the addition. Notice, if I ask you to factor this completely, you have another difference of squares here. B squared plus 4, that's as good as it gets. But b squared minus 4 can actually be factored twice. And so I have b squared plus 4 here, but now I have a difference of squares again, and this would become b plus 2 times b minus 2, and that's all still set equal to 0. I think you can see clearly how you would then solve this. Notice we have a times b times c equals 0. That means this has to equal 0, this has to equal 0, or this has to equal 0. I think you can solve these last two very straightforward. We'll talk a little bit in class on Monday as far as how we would solve that and what would end up happening with that situation and what that means when we're solving quadratic equations down the road in Algebra 2. Again, the main idea is factoring the difference of squares, seeing that pattern a squared minus b squared becomes a plus b times a minus b. As long as you got these notes, as long as you watch the video, you'll be ready to get a little extra help on Monday and be ready to go. Good luck.